topic today is we're studying Riemann surfaces, so this is compact Riemann surface. We don't know many examples. And we're interested in the possibility in examples. We don't know many examples. Embedded in P2C. Remember that this Riemann surface is a one-dimensional complex manifold, so let's emphasize this is one-dimensional. And 2 here means that this is two-dimensional. And this is, we know, is the projectivization of C3, so we always lose a dimension when we projectivize in vector space. Okay, that's the setup. And this is the easiest way of finding interesting examples, and I want to talk about that. So I will write Z1, Z2, Z3 related to standard coordinates in C3, and I will call it standard homogeneous coordinates. Recall what that means. We have, it means, for example, if we use the standard open sets, so in C3, minus 0, we have points here, then we have a point here, Z1, Z2, Z3, in the subspace W, which is a line in this case, and there's a point in projective space. And then we have also the point 2 times this. It doesn't matter. It's just the different bases of that vector, one-dimensional vector space. 2 times 1. So it's the same thing. So what it means is standard homogeneous coordinates. We have these coordinates upstairs. This is contained in C3. It means that if the line is not in Z1 equals 0, so we have upstairs, we have V1, is where Z1 is not equal to 0. And so if you have a W which is not contained in V1, then we can divide by Z1 the basis, because Z1 is not equal to 0. We can divide by Z1. So what that means is that this on U1, which is the open set of lines where Z1 is not equal to 0, on U1 I can use coordinates Z2 over Z1 and Z3 over Z1. These are exact coordinates. Right? I can divide by Z1. So I can always scale this by Z1 and go to some point, for example, well, it doesn't matter, go to some point here. And I called this yesterday Zeta 1, Eta 1. That's coordinates on a very big open set on U1. Okay, so that's U1. And then I do the same thing. I have homogeneous coordinates, so that means on U2 I have coordinates where I can divide by z2. So on u2 I can divide by z2, so I get zeta 1 divided by z2, z3 divided by u2. And I call these coordinates on u2, I call that c2, eta 2. On u2. This is getting to be boring, but I want to do it once. And then on u3, homogeneity says I can divide by something if it's not 0. I can divide by u3, so on u3, those are the lines that are where z3 is not 0. So I can divide by z3, so I divide by z1, z3, z2, z3. And then I call these coordinates zeta 3, eta 3, and u3. Okay, that's it. So those are 3 coordinate patches on P2. Okay. And now a key picture. So you have to always have a key picture if you're going to understand something, right? And that is the following. And we have projective space, this is the blackboard. And now I have U1. Now U1, the coordinate, I'll write it here as coordinates, it's zeta 1, eta 1. And there's a special point in U1, namely 0. And 0, I'll write it here as zeta 1, eta 1 equal to 0. That's the coordinate. But if you don't mind, I'm going to write it in homogeneous coordinates. I just think homogeneous coordinates, I write it as the point 1, 0, 0. So that's the unique point, which I often think of as the origin in projective space. Okay, and now, fine. So, yeah, okay. And now what I want to do is I'm interested in what is missing. So this is just the picture of U1, and what happened? What is the rest? So the rest of this thing is at infinity. So get used to me talking about infinity. And this picture means this. These are the lines where z1 equals 0. Yeah? Get used. So remember what these things are. This point 1, 0, 0. I go upstairs. And let's go upstairs in the z1, here's z1, z2, and z3. The point 1, 0, 0 means that I took as a basis of this one-dimensional space the point 1, 0, 0. Right? So we're really talking about this line. Okay. Now there are a bunch of bad lines here from this point of z1, namely the lines which are contained in the plane z1 equals 0. Remember what this is. z1 equals 0 is the complement of that plane, contains all the lines in so what is the situation here? Where on U1 is I didn't write it. Oh, here's V1. This is upstairs. This is the picture of V1. V1 is where these are the lines where the basis that we chose is not 0. And the rest of the lines is where the basis Z1 is 0. So those are the lines, those are the lines in this plane. Right? Those are the lines in that plane. So I hope you see, those are the lines in a plane. This is just a copy of P1. This is a copy of P1 of the plane, the projectivization, the projective space of the plane where Z1 equals 0. Right? Those are the lines that are contained in that plane. That's the complement of that open set. Right? Okay. So now, and this big thing here, U1 is a copy of C2. And we have all of the lines in U1. We have, for example, let's see here, let's take this point here. Maybe this point is something like, I don't know what this point is, it maybe is, Z1 is equal to 0, so maybe it's this point. Okay? And probably this is, it depends what this line is, but probably it's this point, 0, 0, 1. Right? Those are the key axes, right? These are the key axes. So what is this thing? Maybe I draw it in pink. Maybe I draw it in pink. This is a line. Well, this is a projective line, so it's all linear combinations of these 2 points. So let me write it down, all linear combinations. Zeta times, well, I don't know. Zeta I've used too many times. T is a good parameter. T 0 times this point plus T1 times this point. Now maybe you know, I like to write a line like that. You can see this is what we call like a homotopic parameterization of this line. So this is T0, T1, 0. And these things arrange here in projective space, T0, T1. Both are not 0, that's the key condition. So you have a point here in the middle of this thing, which is T0, T1, 0. This is the line from this point, 1, 0, 0, to the point 0, 1, 0, all linear combinations. This is stuff for the 8th grade in high school, or below. It's all these combinations. And these things are varying in projective space, so they can, any combination you like. This is this P1. This is the, I need an orange point. This obviously, these are the points you get. This line here is the point, this is the lines in the plane, or bases in the plane, what's common here? Z3 equals 0. Right? Those are all those 9. Okay, so where is that picture? Z3 equals 0 is here, and we have all those lines in here, and those lines correspond to this point, this thing. I can see this is new for you, and I guarantee you, if you're in Italy, you learn this in high school and freshman year in college, and you get used to it. In Germany, you don't learn it anymore, so it's now time for you to learn it. Okay, this is projective space, so it parameterizes the one-dimensional subspaces. Yeah. It's good to use homogeneous coordinates because it means we can divide by anything that's non-zero. Then we ask, what the devil is this line? This line, well, this line, a projective line, is a plane. It's the space of all lines in a plane. It's not very hard to see that the general point here, this is 0, this is 1, 0, 0, this is 1, 0, 1. So the general point would be, the general point, let's write the homotopy down, is S0 times 1, 0, 0 plus plus S1 times 0, what's that point there? 0, 0, 1. So this is equal to S0, homogeneous coordinates 0, 0, S1. This is the plane. The general plane is this runs in P1, because this is homogeneous in P1. This is the plane Z2 equals 0. That means if we go to this plane Z2 equals 0, those are all the lines in Z2 equals 0. All right? Okay? Yeah.
Do we say something about T0 and T1 that they add up to 1 or something?
So you're used to thinking about real parameters, and maybe here they are complex, of course. And I understand why they add up to 1, because you're thinking of something like what we call a homotopy from one point to another, but no condition. These are all linear combinations of these two vectors, and what that really means is, and also you see the end result is this. Well, you asked about T0, it's here, yes. And that means these things are free to move in projective space, in P1. Because I can multiply by lambda and it doesn't change anything. So, okay, if you just think homogeneously, this is a point in projective space. So, T0, T1, the only condition is that both are not 0. Because if you multiply by both 0, you kill everything and it's not allowed. Right? Okay. So I'm just parameterizing the lines as linear combinations in one space. Here, if you look at it as projective space, here's the projective line. This is the projective line. And this is the projective space of a certain plane upstairs. And upstairs, the plane looks like this. And then here we have all the lines in the plane. Well, if you have a plane upstairs and all the lines in the plane, what you get is the projective space of the plane. One dimension less. Just get used to it. Ha! I just quoted Mick Mulvaney, who was the assistant of Donald Trump, who when Donald Trump bribed the Ukrainian, Mick Mulvaney went in the public and said, just get used to it, he does it all the time. So all I can say is that I don't mean that. I mean, get used to practice with this picture. It's a beautiful picture of going from lines to points. That's all I'm doing. I'm going from one-dimensional subspace to points, right? So if you have a one-dimensional subspace in projective space, it's compact, it's projective, but it corresponds to the space of all lines in some plane. And so, for example, if you have something back, oh, no, that's interesting. What the devil is this here? What the devil is this here? Let's get this right. Since you haven't had any experience, I'm happy to talk about this. This is the plane Z1 equals 0. Oh, well, there it is. Z1 equals 0. So I can even write the typical homogeneous coordinate of STU, I don't know, Z1 equals U0, U1. Same argument. Yeah? I hope I got that right, yeah. So you have all of these lines, and of course you have the connecting line. Well, let's see here. Oh, good, I have another color. So I have all the connecting lines. I have that line to that. So if I take a point here to the point here, is what Nicholas asked. Is that really a homotopy T0 plus T1 equals 1? No, it's just some linear combination, but with the condition that both are not 0. Yeah, and so that is. I really do think of moving projectively along here from that point to that point, and that's a copy of P1. Okay. So if you see a professional geometer talking about projective space, you will quite often see him or her speaking of a triangle. And so there is a triangle. So there's a triangle, here's a triangle. This is projective space, this is a triangle. And you have to understand this is not an exact picture. It's just, right? And so you say, okay, maybe this is the line, to make it consistent with my other picture there, I had a lot of stuff on that other picture. This is the line z1 equals 0. And this is the line, okay, if you like, this is the line in projective space where z1 is equal to 0. But that means all the one-dimensional subspaces in the principal bundle which have a basis in z1 equal to 0. And here is z2 equals 0. And here is z3 equals 0. Okay, that corresponds to lines sitting in certain planes. Okay, that corresponds upstairs to the planes that I've written there. It's a terrible picture, but you understand what I mean. And then you have various things here. You have, quite often I set this up to be the origin. So this is the, yeah. I think maybe I wrote something wrong here. Z1, what's the plane at infinity? Z1 equals 0? This is the point. The plane at infinity is 0, Z1 equals 0. The plane here is this, I hope this is the plane Z2 equals 0. No, Z3 equals 0. I don't like the way I've set this up. Isn't this correct? This is in my picture. Why should I use the same picture? I'm going to draw the picture Z1 equals 0, Z2 equals 0. No, now I know. Now I know. When we're in elementary mathematics, we have the Z1 axis and the Z2 axis, right? And the Z1 axis is Z2 equals 0. Yeah? Z1 axis is Z2 equals 0. So I think we should make this Z2 equals 0. That's the Z1 axis. And this is Z1 equals 0. And this, the plane at infinity will be Z3 equals 0. Projected line at infinity. So this will be the point Z2 is equal to 0. This will be the point 0, 0, 1. I like this point. Z2 is equal to 0. And Z1 is equal to 0. That's good. Because Z2 is, that's the origin. Right? That corresponds to this point here. That's the origin. That's good. Z1 is equal to 0 and Z2 is equal to 0. And then in this point should be on this line. So Z3 is equal to 0. And the line is Z2 equals 0. So this should be the point, well, Z3 is equal to 0 and Z2 is equal to 0. So this should be this point. That's good. I like it. And this point over here, this point should be, well, what is 0? So it's on this line. And it's also, so Z3 is equal to 0. And Z1 is equal to 0. And it's this point. Now that could not be easier. Right? Right? That could not be easier. And any professional geometer knows that picture at nighttime and tells it to his 7-year-old grandchild who repeats the picture. Well, there it is. You have projective coordinates. You see, this is affine. This is vector space coordinates. This is sort of projective coordinates. These lines. Okay. Okay. And so, from this view, all of these things are copies of C. I'm going to emphasize this. If I take out infinity here, this is a copy of C. If I take out infinity here, I said it's a line, it's a projective line, but if I take out infinity here, it's a copy of C. Okay? If I take out infinity. So that tells you how to think about projective space. So P2 is this, so the view of P2, of P2C, is this I'm going to call the origin. is stand at the origin, So I'm standing at the origin, you understand, I'm standing at the origin, and I'm looking toward infinity. Right? And I'm looking toward infinity at all possible ways. There are many ways to look at infinity. So I look at infinity and look toward infinity. Look toward infinity, and I'm going to write a word here that has no meaning, but it has intuitive meaning, in the direction in some direction. And now this is on the line C3 equals 0 out here. In the direction I'm going to write this, I'll write pink. In the direction A, B, 0. So I'm looking at infinity at A, B, 0. Crystal's looking at infinity at another point. You other guys are boring. You only look at the standard point, right? Well, that's looking at this axis or this axis. And maybe Crystal and I want to go out here on this. It's a P1, right? So what you do is you add all the points at infinity, and you get projective space. So look in the direction and add infinity at that point. And add infinity in that direction. Isn't that clear? And now, excuse me, you should talk about something really elementary, not be fancy with a two-dimensional. Let's look at the Riemann sphere. What is the Riemann sphere? Well, it's P1C, but some of us call this C bar, which is C plus infinity. It means you're standing here and you only have one direction to look at infinity. One complex direction. So you stand at 0. And there is no choice. Only one way to go to infinity along a line. Along a line, because there's only one line. One line. You got it? Yeah.
Do we also say something like plus and minus infinity? Because if you say
I'm glad you asked that, because you started real analysis. Yeah. And and in real analysis, we do something, we hook on either plus or minus infinity. He mentioned plus or minus infinity. So this is Nicola's line. He's standing at 0. And he told me there are two ways to go to infinity. Right? So he says you can add on somehow plus infinity and minus infinity. Right? That's what you said. And I know in analysis 1 we talked about plus infinity and minus infinity. And the reason is there's an order here. There's a direction standing here. There's an orientation. It's oriented. So R has two orientations. Then you can go from left to right or from right to left. And that's telling you the two different directions to infinity. Yeah. So, and really, then you compactify. So R compactified is a compact interval from minus infinity to plus infinity. Right? That's what you were talking about. What the devil is this thing? Now, we're doing this over the complex numbers, and there is no orientation. There is an orientation, but it's canonical. There is an orientation, the complex number has an orientation. So it's canonical, so there's only one way to go to infinity. That's the way you should think about it. Okay? So this is right. And anyway, one thing, you may make a good argument for this compact interval, but it's not a manifold. Right? The compact interval is certainly not a manifold. So it's horrible. Right? What does it mean? That an open neighborhood, well, okay, some of these people argue an open neighborhood of plus infinity, an open neighborhood of plus, it's not so bad, is from A to plus infinity. That's an open neighborhood of infinity. I don't know, I don't like it. So what I do is I go to the compactification of S1. So I compactify the real numbers, but I fix an orientation this way, and I compactify with the one-point compactification of S1. Right? You know that all the time, e to the I theta or something like that. Right? So this is for me this is a good compactification of the real numbers. Although I completely agree. In real analysis, we talk about going to plus infinity and minus infinity. And then Riemann realized we go only to infinity here, so he only adds 1 point and gets the Riemann sphere. And the Riemann sphere is, of course, P1C. Okay. Okay. I can't explain it much better, and I recommend that you think about it. By the way, I never had a course in this subject. I never had a course in almost any subject because I hated courses, and I just enjoyed doing things myself. And I think that's the way you learn things in life. By talking privately to people and then going home. Prabhat and I had some conversation just now. It's not a course. I just told him how I think and what to think about and what to check. Right? And then I think you learn on your own, right? I mean, but you need to talk to people. It's a human science, right? You need to talk. And you need to see my intuition. I mean, you need to see how I'm thinking. But then go home and think about it yourself. Okay. And now, here we go. Equations in P2C. Well, I'll give you an equation. The simplest example, e.g. Z3 equals 0. We talked about this equation. What we talked about in this equation here is here. Here is Z3 equals 0. That's the defining equation for this line. The set of points, which is of the form S0, I don't know, S1, 0. All possible such points. This is an equation, Z3 equals 0, but you should ask, as you like to ask, Z3, or remark, Z3 does not make sense on projective space. Does it? It does not make sense. It's a coordinate upstairs in the vector space, right? So that really means that we're talking about a plane upstairs. Nevertheless, we've seen that makes sense. Well, then we may be more general. Let L be a linear function. And if L is a linear function, then L equals 0, any linear function. This is a linear function. L equals 0 makes sense. Because if it's a, let's write it down. This is the set of Z1, Z2, Z3, such that, maybe I'll write down L, the linear function. A1, Z1, plus A2, Z2, plus A3, Z3 equals 0. Right? If L is that linear function, here's the linear function L. Right? L equals 0. Well, that's also a linear function, Z3 equals 0. Right? Well, what does that really mean? That really means, we get tired of what this really means. This means upstairs, it means upstairs, L equals 0 is some plane upstairs. Right. Here's the plane L equals 0. That doesn't faze you. You don't worry about writing down a plane in C3. And now we're talking about all of the lines in this plane, all of the vector spaces in this plane, all of the bases of one-dimensional spaces in this plane. We're talking about all those lines in this plane. And when we parameterize this thing in projective space, that's the line. This is, well, okay, this, for example, that would be L equals 0. Okay? It's a line, it's a projective line. Okay? Let's try something else. That's the first example, L equals 0. So example 1, linear. Well, let's look at the full polynomial ring on the vector space. The linear functions generate this polynomial ring in an obvious way. Right? You just multiply them up and get higher order terms. So, as we have seen, if you look at all those polynomials, we saw yesterday that this is the direct sum over all k of the symmetric k-fold tensor product of the linear functions. That's what we just did. We get the linear functions and we multiply them up. That's a fancy way of writing. These things are the homogeneous polynomials. These things are the homogeneous polynomials of degree k. I'm just writing that down in a precise way. What is a homogeneous polynomial? But let's just write this down to simplify notations, direct sum over k of the homogeneous polynomial. And the way we write it this way is with k here. Okay. And if you take a homogeneous polynomial of degree k, and then you multiply inside by lambda, that means you're changing bases upstairs, isn't it? Z is upstairs. You multiply by lambda, you want to know what the devil happened to the basis. Well, the basis goes to Z times lambda. What happens to the polynomial? It doesn't change much. Right? It doesn't change much at all. It doesn't change much at all. In particular, if you multiply this by lambda, the 0 set doesn't change. So if you look at P equals 0, right? It doesn't matter, left-hand side is 0 or the right-hand side is 0, right? P equals 0, it doesn't matter. This thing is C star invariant, and that means that if you have a point in it, you move it by the whole line is in it. You have a point in it, the whole line is in it. If you have a plane upstairs that's a plane, the whole line is in it. Planes, you don't need to talk about that because it's linear. But if you think about it, it's the same calculation. The L of lambda times Z, well this is just lambda times LZ. right? It doesn't change if it's linear. It means, what this means is that if you have the line Z here, here's the basis here, and here's lambda Z, it means if Z is in this thing, where that's 0, then that's the same thing as lambda Z. It doesn't matter. That line is in that one-dimensional space. These bases are in the plane, in this thing. Okay. And that means that we have a new picture. I guarantee you these pictures are a very nice way to look at things. Well, let's see. Let's see here. Let's look. L equals 0 is a plane. L equals 0. It's a plane. And you're going to hate me because I'm not going to call it a plane, I'm going to call it a cone. You say it doesn't look like a cone, but it is a cone. A plane is a cone. A plane is a cone because here's 0 in it. And if I take a point in the plane, I take the entire one-dimensional space that's in it. Isn't that the definition of a cone? Yeah? A cone through 0. This is the vertex of the cone. This is the vertex of the cone. Right? If I take another point in it, then the entire line is in it. If I take another point in it, then the entire line is in it. Right? It's a cone. Right? It's a cone is a cone. It's a linear cone. It is the only smooth cone. It is completely smooth at the origin. Now, if you take another cone, let's take. I'm thinking every time I use the word cone, I'm thinking of a friend of mine in the United States whose name is Cone. This is Joe Cone, who's a very good mathematician at Princeton, and now I'm thinking of a cellist in Paris who's married to the daughter of my maestro in mathematics. His name is Cohen, C-O-E-N, Cohen. It's the same as cone. And I think it means, in maybe English, maybe it means coin. You have to look at the old this is primarily Jewish, these are all somehow Jewish names, in Cohen, so on. But when I think of my friend Joe Cone as a wonderful mathematician, or the cellist in Paris, who is very good also. He plays Baroque cello as well. So now I'm going to take another one. Let's take the simplest one. Z1 squared plus Z2 squared plus Z3 squared. Okay? Why not? Yeah. Why not? That's going to be the polynomial. Let's call this thing Q because it's quadratic. Okay? Let's call this thing Q because it's quadratic. Now what did I just say? If you take any point in this thing, here's the point A in this thing. So it's A1, A2, A3. Right? I stick them in here, and then I multiply by lambda A1. So I change bases. A2, A3. Yeah? These things are in this cone. So the A1 in this A2, A3. And there they are. And here's 0. Then in fact, this thing, where the devil are we? Oh. Where are we? I'm upstairs. I'm upstairs in the principal bundle. So I have this full line in here. Just like I had the full line over here. And then you're going to get tired of me doing this. So if I have another one here, maybe I have another one here. This is B1, B2, B3. That is upstairs. All of this picture is in upstairs, right? These are all the lines upstairs. Okay. Well, that's in C3. Now, what did I just tell you? P3 is the compactification of C3 if I stand at the origin and look at infinity in these various directions. Well, that was P2, but I'm sure you're capable of doing P3, right? It doesn't matter. You take the standard chart. Here's the chart. Okay. What the devil does this mean that we're in C3? Let's draw the picture. We're in C3, so we're picturing C3 in P3. Right? And then so you say, what is infinity? Infinity is the line Z4 equals 0. Why not? Z4 equals 0 is, well, a line, a linear equation. That means this is Z4 equals 0. So a general point here is anything Z1, Z2, Z3, and 0. That's any point at infinity, you get it? And of course, now it's going to get hard for me, but actually, didn't I just tell you that this is going to be a P2 at infinity, because it's just, so this is the P2 at infinity. These are all the lines at infinity. You see there's a P2 at infinity. So that's really P2, that's a triangle. Right? At infinity. Well, this is Z1 equals 0, this is Z2 equals 0, this is Z3, this is Z3, and so on. This is a triangle at infinity. Got it? That's P2 at infinity. And now somehow we have the origin. This origin is in C3, which I'm regarding as being in P3. Right? So really, these points, these in the C3, if I want to regard this as being in C3, I compactify. So this is going to be wait a minute. Wait a minute, are we going to do this? Yeah. Right. So this is P2, and this is C3, and this C3, the typical point in this C3 will be homogeneous coordinates Z1, and I'm going to put it in here, A1. I'm going to put in here the affine coordinate A1, A2, A3, and 1. Because if I can do this, if it's not 0, I'm outside of this, I get to put 1 in here. That's here. And then I have in my picture lambda A1, lambda A2. They're all the same. Lambda A3 and 1. This is a picture of V upstairs. This is C3. So here we go. Wow! So upstairs, I had the equation in this affine space of Z1, Z2, Z1 squared plus Z2 squared plus Z3 squared equals 0. That's a cone, and through every point I have a line. This is upstairs. And this line intersects infinity in one point. This is where Z4 is equal to 0. And in infinity, and now I have to draw it, I probably will make a mistake, but it will be more or less this. So this is the equation Z1 squared plus Z2 squared plus Z3 squared equals 0 in P2 at infinity. And upstairs, when you look at all the lines, remember I said upstairs, you look at all the lines in a plane. Okay? Upstairs, I'm looking at all the lines in this cone. Now this Joe cone looks like this, so I'm going to draw it again nicely. Here's the projective space at infinity, and here is Q in that projective space at infinity, so I'm going to write this Z1 squared plus Z2 squared plus Z3 squared equals 0. And that's in the homogeneous, and here's the cone over. And this cone, this is the cone over Q. Now, this is all new for you, so I really want to repeat this. Okay. This is fundamental that you see this picture. Absolutely every complex analyst in geometry has it in his head. Okay, ready? If I have a plane upstairs, you know where I am when I say upstairs. And I take a point in the plane, I have the line through that point, and I regard that point as a basis, if you like, for that line. So all of the, and if I change bases in that line, I just move along the line. I mean, that's a stupid thing. So all the lines in this plane correspond to a certain set in projective space. Right? Well, it's all the lines in one plane. Well, I mean, that's the projective space of one dimension less, because it's the lines in a plane. Right? P2, that's P of C3, that's all the lines in C3. But if I go into a plane in C3, I've jumped into all the lines in that plane, so I lower the dimension. So that gives me, if I jump into that plane in upstairs, I get downstairs in projective space a line. And it didn't bother you at all. Right? Now, I say to you, that's just linear. So the first thing you do in your stupid questions is you say, well, this stupid professor, he talked about linear, what about all the other stuff? And then you ask yourself, what's the other stuff? And you say, other polynomials here. And you say, okay, I want to find out where this makes sense for other polynomials. And immediately, without locking yourself in the closet, you immediately know that you should look at homogeneous polynomials. Right? Because if a point satisfies a homogeneous equation, then you change basis and it still satisfies the same equation because it just comes out to the front, right, that lambda. So homogeneous things are playing the key role here. So we decide to look at an example, namely a quadrant. Okay? And now I jumped on you, I'm a little bit unfair. I said I want to consider upstairs and downstairs at the same time. Okay? So what I said, what I'm going to do is I'm going to look at P2 as being in P3, yes, as the line as the P2 at infinity, and then upstairs, which is C3, I'm going to put in downstairs as the open chart downstairs is the complement of that P2. This open chart is the open set. This open chart downstairs is the open set where the last variable is not 0. This is U4. And so this point is the origin 0, 0, 1. Wow, that's just the origin of that vector space. So this is all this vector space. So when you have a nonlinear equation, upstairs you don't get a plane. That's not very surprising, right? The zero set of a quadratic equation is not a plane. It's a cone upstairs. And here's the cone upstairs, and it's the cone over the quadric downstairs, the quadric curve downstairs, which is a smooth manifold non-standard. Okay? So, let me state a theorem. I state the theorem. Which is not too hard to prove. Every algebraic subvariety, and I put this in quotes, of P2C is the zero set of a homogeneous polynomial. Okay, there are two words which I didn't revise here. This theorem is not difficult. So homogeneous polynomial. So we look at homogeneous polynomial in C3 and standard coordinates of degree k is a general thing that looks like this. Sum ai z to the I, so that the length of I is equal to k. I'm sure you know multi-index notation, right? Right. So just make sure you know z to the I means z1 to the I. Well, we're in P3, so it's z1 to the I. 1 is z2 to the I, 2 z3 to the I3. I3. That's what is a homogeneous polynomial. Okay. And if you have a homogeneous polynomial, it's completely clear that if you have a homogeneous polynomial P, then P of lambda z equals lambda to the k P of z, and so that means x is equal to P equal to 0. It's certainly a reasonable set, and it is algebraic in nature because this is an algebraic equation. Whatever algebraic means. By the way, whatever algebraic means was not precisely defined until, I would say, Grothendieck. Okay? So whatever people would say it's defined by polynomials or something like this. Okay? Right? Let me give you a definition, which is not a good definition, but a definition. A set is algebraic if you have a covering, so that on that covering, this set is equivalent to something algebraic. Yeah. What is something algebraic? It's equivalent to a subset of Cn, which is defined by polynomial equations. Okay? That's not a bad definition, right? Something is algebraic if it's locally algebraic. Locally algebraic, it means a subset of C, it means very big, a subset of Cn which is defined by algebraic equations. Algebraic equations mean polynomials. Okay. That's what this means. Everything is just the zero set of a homogeneous polynomial. Yeah.
And what is a subvariety?
Hmm?
What is a sub?
Oh, I'm sorry. So algebraic, I've more or less said this. That means it's locally defined algebraically. See, it's not clear. A homogeneous polynomial is a global guy, right? It's just some global thing. So it means it's locally algebraic, just like it's a local manifold in Professor Perra's quote, right? Submanifold means locally defined by C infinity equations. Holomorphic submanifold means it's locally defined by analytic equations, holomorphic equations. Algebraic means it's defined by algebraic equations. This theorem says it's defined by one equation. Not bad. Not bad. But it's not bad at all. So let me just some indication of the truth. I have to stop now. Of the truth. So, you know, I'm American by birth, and we have this horrible president of the United States who lies all the time. So I like to tell the truth all the time. Some indication of the truth. Every analytic, complex analytic, subvariety. And now this is, I'm allowing singularities here. So I just mean locally defined by holomorphic equations. Okay. Is the zero set of finitely many homogeneous polynomials. Of course, I mean subvariety of projective space. It's a zero set of finitely many homogeneous polynomials. You are too inexperienced to understand that that is a mega theorem in the modern lingo. But it says that everything analytic is in fact algebraic. Every complex analytic subvariety, I mean, remember what that is. Here's something, a submanifold or subvariety. Locally, it's defined by a bunch of holomorphic functions equal to zero. The statement is global. The statement says that every subvariety like this is the zero set of finitely many homogeneous polynomials. I mean, global things of this form. Yes? So as you see, this is an embedding of complex manifolds of a certain type in algebraic geometry. Okay. That is why there is this huge overlap of these two subjects. Okay. Okay. And I will. Oh, by the way, you should know a name of this theorem. People call this Charles' theorem. There's a long history of this theorem. Many people make contributions, but the final proof maybe is in the 1950s. So it's a new theorem. It's a very deep theorem. It says in certain aspects, complex analysis and algebraic geometry are the same thing. Okay. And it's the same thing, study of homogeneous polynomials. Okay. And that means the study of things like this, and that means the study of cones over them, and that's what I'll talk about in the next lecture. So I'm way over. Am I way over time?
No, 7 minutes before.
We
have 7 minutes.
Oh, we have a little bit. Yeah, we have a little bit more time. Yeah, but I think it's a good stopping time. Let's stop now, and then try to meet right at.